Greetings. So, in our previous class, we discussed the Young's double slit experiment and came across some very mind-boggling, situations. First of all, you get interference pattern that itself is incredible. You have two sources of light, and then there are places where you don't see any light at all. Whereas classically you expect double the amount of light over there. So you have these fringes, and then you can make them appear, make the fringe pattern appear or disappear depending on how you perform the experiment. So if you choose to know from which slit the particles have come, then you destroy the interference. If you use an eraser to erase this information, the interference pattern reappears. Even if you perform the a delayed choice, if you execute a delayed choice, you choose to lose that information much later than the time it would take for the particles to reach the detector, even then the interference pattern is lost. It is because of the orthogonality of the two states of the which way experiment. So, basically I am going to discuss how a system changes, how it evolves with time, and that is in fact a fundamental question in mechanics as to how do you describe the state of the system and how does it evolve with time. So, the time evolution we have to study, and then there are other transformations which are involved, not just changes with respect to time, but here you have these three situations. What happens if you displace a system? Okay? So, translational displacement. Likewise, you can have a rotational displacement. Okay? And then you can have an evolution with respect to time, that you are not displacing it nor rotating it, but you want to know what will be the state of the system tomorrow, or ask what was it yesterday, right? So these are the three operations that we are concerned with: translational displacement, rotational displacements, and then temporal evolution. Evolution is a function of time. Okay? So if you know the state of a system at time t0, which you see at the bottom of this slide, then you ask, what is the time evolution operator u, which will give you the state of the system at a different time t. It could be a later time or an earlier time, but at a different time t. So typically we are talking about evolution. We are interested in knowing what will happen in the future, although a lot of people are interested in what happened in the past, but that information is also sitting over here. All right? So, when you talk about translational displacements, so we know that the translational displacements commute. It doesn't matter whether you first go east and then north, or first go north and then east and reach your school. Okay? That's actually the picture of the school I went to. So you have these translational displacements which commute as a result of the fact that the generators of these displacements, which is a linear momentum operator. So these linear momentum operators px and py commute. So orthogonal. So they generate an abelian algebra, they commute. But finite rotations do not commute. Okay, so you are going to expect some differences when you perform rotational displacements. So finite rotations do not commute, but if you have infinitesimal rotations, then they do commute to order epsilon square, where epsilon is an infinitesimal rotational angle. So we are going to discuss these infinitesimal rotations today. So, you consider an infinitesimal rotation about the x axis in this figure. This is a Cartesian right-handed coordinate system, and you perform a rotation through an infinitesimal tiny angle delta phi about the x axis, and you can represent the new vector, new position of a point which is rotated by this vector r subscript r as r plus delta r, and you can see from this figure that this is nothing but delta phi cross r. So, it is a cross product of this in the limit that delta phi goes to 0, right. So, you can write this cross product as a determinant, and you can write the transformation from xyz to the rotated coordinates xr, yr, zr through this matrix equation, and you can write this matrix as 1 0 0 0 1 minus delta phi and delta phi 0 delta phi 1, because this is the rotation matrix for rotation about the x axis. And to order epsilon square, if you take the cosine theta and sine theta, you expand them, all right, and retain terms only up to the quadratic terms, then the cosine theta is nearly equal to 1 to order epsilon square, and sine theta is nearly equal to theta. The next term will be theta cube, which is smaller than theta square, so you ignore it, right. So, this is your situation with respect to coordinates transformations. Now, you ask, how will a wave function transform? Because the wave function is a function of the coordinates. You know how the coordinates transform under rotation. So, now we are asking, how does the wave function transform? So, if it has got some shape, then it is rotated and you get a new orientation, but the orientation is such that the actual shape is preserved. So, there is a symmetry involved, that is completely preserved, but only the relative orientation is turned. So, that is a kind of rotation that we are talking about, and we are asking, how will you describe the rotation, the effect of rotation on a wave function. So, let us say that u is a rotation operator through an infinitesimal angle delta phi, and infinitesimal angles can be represented as vectors, not the finite angles, right, because that's exactly what we have been talking about. So, an infinitesimal rotation angle, which I denote as a vector, and this operator gives you a new state when it operates on a state vector alpha. So, this is the quantity we are examining. We insert a unit operator, which we can always do, right. So, this is the resolution of the unity, and you can see that this rotation operator will turn the coordinate r to r plus delta r. Okay. So, this is just a scalar. So, the rotation operator is not going to do anything to this, it is just a complex number, right, and this is the new integration that we get, and we can write this integration instead of, this is a sum over r plus delta r, we can also do it the same integral as a sum over r prime, where r prime is r plus delta r, right, and then the integration becomes the dummy label changes from r to r prime. It does not matter because you are picking up every single point in the whole space, okay. But then look at what happens to the wave function over here. This is the wave function, this is the probability amplitude that a state alpha has at the coordinate r, whereas here it is the probability amplitude of the same state, but at a coordinate not at r prime, but r prime minus delta r. So, it is a neighboring point, okay, which is infinitesimally close to the previous point. So, you can do a Taylor expansion of this. So, this is what you get, all right. So, you can do a Taylor expansion. This is the wave function not at r prime, but at r prime minus delta r. So, this wave function is the wave function at the coordinate r prime minus the difference. So, the difference from in the first order is simply given by the component of the gradient along that displacement. Okay? So, you have a very simple relationship over here that this is nothing but the coordinate representation of the state alpha at r prime minus this difference. So, this is the term which will go in this integrand, and you can write this integrand as integration over r, but now you have these two terms over here which we will separate out on the next slide. So, these are the two terms, all right. And delta r we know from our previous discussion is given by delta phi cross r. So, you write delta r as delta phi cross r. You can always interchange the position of the cross and the dot in a scalar triple product. So, let us do that. So, you swap the positions of the cross and the dot, and now you have the delta phi dot r cross del, but r cross del is nothing but the angular momentum, because minus I h cross del is the momentum operator. So, if you divide it by minus I h cross, and of course, you have to compensate for it by if you multiply you also divide, right. So, when you multiply by minus I h cross, you get the momentum operator, and to compensate for this you divide it by minus I h cross. So, now you have got the r cross p, which is the angular momentum operator which is popping up. So, you put this angular momentum r cross p, which is j over here. So, now you have got delta phi dot j, and the minus I h cross has to be taken care of. So, it is over here. Okay. So, there is a minus sign already over here, and this is 1 over minus I, which is plus I. So, now you have minus of plus I over h cross delta phi dot j, and now you can see that you have got two operators both operating on r prime alpha, which is the wave function. The first over here, it is operated by the unit operator, which is sitting over here, and here the operator is minus I over h cross delta phi dot j. So, you can write this result as the operator 1 minus I over h cross delta phi dot j operating on this state vector, of which this is the unit operator which we had inserted. We can remove it now, okay, just as easily as we inserted it, and you get an operator identity, alpha being a completely arbitrary vector. Then the operators which operated on that must be necessarily equal. So, now we get an explicit expression for the rotation operator. And if you specialize this angular displacements about the x axis, y axis and z axis, you get the three generators of rotations which are the components of the angular momentum. So, you see the components of the angular momentum jx, jy, jz as the generators of rotations. Okay. So, you have these three operators, and if you this is for infinitesimal rotation. So, if you are looking for an operator for a finite rotation, then you have to get this finite rotation out of the infinitesimal rotation by operating the infinitesimal rotation infinite times, right. So, if you do that, it is essentially the limit n tending to infinity of 1 minus I over h cross this the component of the angular momentum operator operated n times in the limit n going to infinity, and that is nothing but the exponential operator that you see over here. So, this is the operator for finite rotations. which we know do not commute. We have discussed this in earlier discussions also, and they do, however, commute to order. Infinitesimal rotations do commute to order epsilon square, finite rotations do not commute. And you can see these transformations by looking how the components of a vector transform to new components when you rotate a coordinate system. So, and you can represent these rotation operators by orthogonal matrices, and rotation operators will have a determinant which is +1, but you may also have some other symmetries like mirror symmetry or parity or inversion and so on, and then the determinant would be -1. So, we are focusing our attention on rotations, and a typical rotation matrix is given by these sinusoidal terms, right, or this is sometimes called as the cosine law of transformation, which is in fact what defines what a vector is, because its components transform according to this law. So, this is the rotation operator for rotation about the z axis, and you can similarly write the rotation operator about a rotation through an angle theta x about the x axis, which is this, and you can expand the cosine theta and the sine theta in a power series and truncate at the second order through all the third order terms. Okay, so here you would have a third order correction in sine theta, which I have struck off, right, and we do the same for the cosine terms. The fourth order term is struck off and so on. So, up to second order you have this matrix representation for Rx, and you have a similar representation for Ry up to second order for infinitesimal angles. So, we are doing an algebra which is correct up to second order, and we have written the rotation matrices for rotation about the x axis and also for the rotation about the y axis. All right. Now, we are going to ask what happens if you perform these operations, rotation about the x axis first and y axis next, or y axis first and x axis next. Do you get the same result? The question is somewhat similar to what we discussed as to what happens when you first go east and then north, or first go north and then east. So, it has some similarity with that, but here we are dealing with rotations. So, let us find that out, and I am not using animation over here because this is very simple matrix multiplication, you can do it. So, Ry first and Rx next is what is determined over here. So, all you are doing is multiply the matrices, okay, and you will get terms in theta to the power 4, for example, or theta cube when you do this matrix multiplication. Retain terms only up to the quadratic terms theta to the power 2, and the result is what I have in the bottom row. So, the rest of it you can work out very easily. So, I am not going to do it step by step. Okay. So, this is what you get when you do Rx first, Ry first and Rx next, and if you reverse the operations Rx first and Ry next, then you get a different matrix. Okay. So, this is Ry Rx, previously you had Rx Ry. So, these are on these two slides the operations in reverse order, and you can just carry out the matrix multiplication, keep the terms only up to order 2 through cube and fourth and everything else, because these are infinitesimal angles. So, they become smaller and smaller, and now you have got the Rx Ry matrix here and the Ry Rx matrix over here, and if you take the commutator, which is the difference of these two, then the commutator is nearly 0, but to order 2 it is not 0. Okay. So, to order 2 it is 0. So, infinitesimal rotations commute to order epsilon square to the quadratic term. Okay? So, this is the result that you need to remember, and you also need to remember that the difference has got the zeros in this matrix everywhere except the second column in the first row and the second row in the first column, all right. And what do you have over there? You have the square of the infinitesimal angle. Okay. So, remember this result because we are going to use it very soon. So, these are the three operators for rotations about the x, y and z axis. We are going to consider infinitesimal rotations. So, all theta x, theta y, theta z all are epsilon, which is a tiny angle, and the commutator is rz epsilon square minus 1. Do you see that? So, you have got the square over here, and if you look at the rotation matrix for rz, not for the infinitesimal angle epsilon, but for its square, then it will have this, you will have 1 in this diagonal element because epsilon to the 4 can be ignored, and here in the off diagonal elements you will have epsilon square, minus epsilon square here and a plus epsilon square here. So, this is nothing but rz epsilon square minus 1. Okay. So, this is a important result that we are going to use very soon. So, the commutator of the rotations about the x and y axis do not commute, but it is given by this difference, which is rz to the angle epsilon square minus 1. You have to subtract 1 from this, the diagonal 1. So, this is your operator for finite rotations, and up to order 2 I have written a nearly equal to sign over here because I am ignoring terms of order theta cube and smaller, right. So, up to order 2 I have this expansion of the operator for rotations, and now if you consider rotations about the x axis and about the y axis and about the z axis, right. But x and y I consider to order epsilon, whereas u are about the z axis I consider epsilon square. So, here instead of I epsilon I have I epsilon square, and here I have epsilon square. So, here I will have epsilon to the 4. Okay. So, what you can see is we use this result and rewrite this expression in terms of the operators, explicit operators in terms of the generators of those rotations. So, this is the commutator of the rotation operators, and this is the same commutation result, but in terms of the generators of those rotations, which are the angular momentum component. So, the angular momentum component over here, this is Rx. So, you have 1 minus Ijx epsilon over h cross, and then you have got the quadratic term coming from the jx square, right. This is Ry. So, I have 1 minus Ijy over here and the jy square and the quadratic term here. All the higher order terms epsilon cube and so on are dismissed in this approximation, right. And then here you know that this is equal to rz of epsilon square minus 1. What is rz of epsilon square? This is 1 minus I jz over h cross square, but this is epsilon square. So, epsilon square comes here, and it is the square of epsilon square, which is epsilon to the 4th, comes here, and the epsilon to the 4th can be ignored. So, this term vanishes. This one cancels this minus 1 because you have to subtract this minus 1, and you are left with minus I jz h cross square epsilon square, right. Now, let us bring this result to the top of the next slide, which is here, it is the same result. Okay. And let us write out this commutator explicitly. So, there are 3 terms which commute with another 3 terms. So, you can write the commutator of 1 with everything else. Now, 1 obviously commutes with everything else, so that will go to 0. You have the unit operator over here also, which will also commute with everything else, right. And then you will have the commutator of this with this, right, and this with this. Notice that in some of these commutators you will have terms of order epsilon square, and in some of the commutators you will have terms of the order of epsilon cube. So, throw those epsilon cube, because we are doing an algebra where our approximation is limited to taking terms up to order epsilon square, right. So, those in which you have epsilon itself, those terms drop out because of this cancellation, and what you are left with up to the order epsilon square, you equate the corresponding coefficients of terms which are of order epsilon square on the left hand side and with the right hand side, and what you get is a very powerful relation, which is that the generators of rotations about orthogonal axis, the angular momentum components along orthogonal axis do not commute. Not only that, they do not commute, they are equal to the generator about the third axis scaled by IH cross. Okay. So, you have got 2 powers of angular momentum on the left hand side. So, you have to have 2 powers of angular momentum on the right hand side, and you get a relation which is similar to the uncertainty principle, okay, because the commutator of position and momentum also is IH cross times the unit operator. So, it is very similar to that, and this is again due to so the manifestation of H cross is consistent with the quantum mechanical pattern that you expect in this situation. Okay. So, if Jx comma Jy is equal to IH cross Jz, then you can do a similar algebra for the commutator Jy comma Jz and Jz comma Jx, and you will get similar relations. You can pack them together, and what you get is a general result that Ji comma Jj is equal to IH cross Jk, but you have to rotate these indices cyclically, okay, Ijk. If you consider all the 3 vectors, then you have got J cross J equal to IH cross J, which is again a stunning result, because the cross product of 2 vectors, 2 collinear vectors always vanishes. Here you are taking a cross product of a vector with itself, and it is not 0, because it is not a vector, it is a vector operator. Okay. So, this is quantum mechanics. If it was just a vector like in classical mechanics, then this cross product would vanish, but in classical mechanics angular momentum is just a dynamical variable, but now it is a quantum vector operator. So, the cross product gives you IH cross J, and this in fact becomes the definition of angular momentum in quantum mechanics. Angular momentum is any quantum operator which fulfills this algebra, that the commutation of 2 components about generators of 2 rotations about orthogonal coordinates or orthogonal axes do not commute, they give you IH cross J, or you can write it equivalently as J cross J equal to IH cross J. Okay. So, these are equivalent definitions of an angular momentum, and we arrived at this using rotations in 3-dimensional Euclidean space. So now we forget about the Euclidean space and the three-dimensional space, and for the rest of our discussion in quantum mechanics, we will have this as our starting point. This we take as the definition of angular momentum. Angular momentum is any quantum vector operator which satisfies this algebra that j cross j is equal to IH cross j. It can be anything, it may not have anything to do with the three-dimensional Euclidean space. And indeed, the electron angular momentum, the intrinsic angular momentum of the electron, which is the spin angular momentum, is an angular momentum only because of this property which defines its angular momentum. There is no analog about rotations in three-dimensional Cartesian space. Okay, it is in some other space which is the mathematical space of the spin eigenstate. So that is a different matter altogether. Okay. So what have we considered? We considered translational displacements, the generators of which are the linear momentum operators. We considered the rotational displacements, the generators of which are the angular momentum operators which do not commute, and we want to consider the temporal evolution as to what happens to a state as time changes, either backward or forward, right. So the translational displacements satisfy an abelian algebra. The generators px comma py commute. The rotation operators come up with a non-abelian algebra, right. And then we are going to ask what happens when time changes. How does a state evolve with time? So this is the fundamental question that we are interested in, and this is given by the Schrodinger equation. A state vector changes with time according to a certain equation, a differential equation, which is the Schrodinger equation, and we have discussed this in our previous classes, right. So this is how the state evolves, and the time evolution of the state is what most of quantum mechanics is about. We are interested in knowing how do you describe this system, whatever quantum system you are working with, how is it going to change with time, and you need to solve this differential equation subject to appropriate initial conditions. And now the question is, you know what is the nature of the Hamiltonian, all right. So the Hamiltonian is typically independent of time, but it does not have to be independent of time, right. It can be independent of time, and then what kind of time dependence does it have? Does the Hamiltonian at time t2, does it commute with the Hamiltonian at time t1? It may or it may not, right. So here is a situation that our case 2 is when the Hamiltonian at t1 commutes with the Hamiltonian at t2, and the third case is when the Hamiltonian at t1 does not commute with the Hamiltonian at t2. Then you get solutions in terms of what is called as the Dyson series. So let us first consider the case 1. Now here this solution is given by this unitary operator. This is the time evolution operator. This time evolution operator gives you the solution to this equation, and you can verify that this solution is correct quite easily by actually putting that operator, expanding it and analyzing it term by term. Okay? So you have an infinite power series expansion of this exponential operator, you put in all the terms. What is this operator doing? It operates on the state alpha at time t0. So let us do that, and you have to take its time derivative, right. So if you take the time derivative of this operator, the time derivative of the first term, which is the unit operator, goes to 0, and from the time derivative of the second term you get minus I over h cross as common, and you get the Hamiltonian itself, right. and you can take the time derivative of this third term, fourth term, fifth term, and so on, and you are essentially getting back a power series. Okay? So now if you multiply this whole result by IH cross, okay, you can see that this is the solution that you had proposed, that the time evolution operator is given by this exponential operator, is in fact correct, because you recover the Hamiltonian operating on the time evolved state. Okay? So this solution is correct. Okay? And if the time difference between the initial state and the final state goes to 0, then of course this time evolution operator becomes just a unit operator, as it should. So this is good. Let us take the second case now. The second case consists of the situation where the Hamiltonian at the two times do not commute, all right, or they do commute, sorry, the third case is when they do not commute. So in the second case they do commute, and the solution is very similar to how it is for the first case. So the details you can fill in, it's exactly the same type of algebra, you can put this in and discover for yourself by straightforward substitution. All you have to take is to take the time derivatives, right, and plug it in, and you can easily convince yourself that this solution is correct. Okay? In the third case it is somewhat complicated, and this is where you get the Dyson series solution, and Freeman Dyson is one of the persons who contributed to the development of quantum electrodynamics, along with Schwinger, Tomonaga, and Richard Feynman, of course, right. And the solution is in terms of the Dyson series, which I will not discuss in this class, but I have discussed it in an earlier course, which is also on the NPTEL website. So if you go to lecture number 26 on unit 4 of this course, you will find the Dyson series solution discussed in some details. So I will not do it over here, but if you are interested, you can go to that lecture and go through it. So this is the Dyson series solution that you get in the third case. So now consider the time evolution of arbitrary states. So alpha is an arbitrary state at time t0, and we are going to consider its time evolution. The rate at which this evolves with time is given by its time derivative, and this rate equation is nothing but the time dependent Schrodinger equation. So let us use energy eigenkets. What are energy eigenkets? These are eigenkets of any operator which commutes with the Hamiltonian. Okay, these are the energy eigenkets, and we will use these energy eigenkets as the basis set in which an arbitrary vector can always be expanded, okay, as a superposition with appropriate coefficients. It's a complete set of bases. It is a linearly independent basis. It doesn't have to be orthogonal, but it is convenient to use an orthogonal linear independent basis. If it is not orthogonal, you can orthogonalize it using Schmidt method or some other method of orthogonalization. So we will consider linearly independent, orthogonal, normalized. Normalization is also a straightforward procedure, you can go ahead and do it, right. And in this basis, you can represent this operator by packing a unit operator after it and another unit operator behind it, right. So this is the resolution of the unity that you can see explicitly in play, and you notice that because these are energy eigenkets, right, A double prime is an eigenket of this operator belonging to the eigenvalue E A double prime, right, and then it does not matter where you write this, and then from the orthonormality of A prime and A double prime, this double summation contracts and you get this result. Okay, so this is how you describe the time evolution if you know the initial state, right. Notice that this e to the minus I omega t, omega is e over h cross, so you can write it as minus I e t in units of h cross or minus I e over h cross t, or write it as e to the minus I omega t, where omega is e over h cross. So, they are obviously all equivalent ways of describing it. So, keep that at the back of your mind, because in our notation we will swap the notation any which way according to our convenience, all right. So, you are often interested in studying additional properties of the quantum system, right. So, you have studied some property which you call as A, then you want to study another property, and you can do it only if it is compatible, if that measurement is compatible with the previous one, right. So, if you have performed a measurement of A, it is not guaranteed that a measurement of C is possible. That depends on whether or not C commutes with A, right. So, we consider those possibilities which are compatible with each other, so that you get a complete set of commuting operators, the CSCO in Dirac's notation, which we have used in our earlier discussion in this lecture course, right. And we are dealing with the first case. The second case is similar, as I mentioned, and the third case is a little more complex, but I have dealt with separately in a different set of lectures, right. And you can handle even time dependent perturbations using the same methods as the case 1. So, we have got this result just on the previous slide, or the one before that actually, right. So, this is how the time evolution of the state is defined by this operator. So, if you have an initial state, you expand this in the complete set of bases of the energy eigenkets, and the expansion coefficients are the C, which are nothing but the projections or the shadows of the state alpha at time 0. Time 0 is what I consider as the initial time t0, all right. And the projection of this on one of the basis sets, it is actually the dual conjugate vector in the basis, and this is the expansion coefficient. If you consider the state at a later time t, then you have got a similar expansion, you are using the same basis set, but the expansion coefficients are now time dependent. So, now you are asking, what is the relationship between the expansion coefficient at time t, which is here on the right, to the expansion coefficient at time t0? How are these two coefficients related? Okay. So, this is the question we are now examining, because that will tell us details about the time evolution of the state. Okay. How are these coefficients related? So, these are the two coefficients. This is the coefficient at time 0, this is the coefficient at time t, and we are asking how are these two coefficients related. You have got the initial state and you have got a time, this is the state at t0, this is the state at a later time t, which is why you have got the time evolution operator from the time 0 to a later time t. Okay. And this operator is given over here, so we replace it by its expansion here, and now simply carry out this algebra, and now you see that you have orthonormality between A prime and A double prime. So, that gives you a Kronecker delta. You can contract the sum and you see that the coefficient of the state at time t is given by the coefficient at the time 0 multiplied by this. Now, this is a very important result. It is simple but extremely important. that the coefficient at time t is related to the coefficient at time 0, it is actually the same. The modulus is the same, the change is only in the phase. Okay? And this is an extremely important phase. This is called as the dynamical phase, because it tells you how the dynamical system evolves with time. And subsequently, I am going to introduce another phase which will be called as the geometric phase or the Berry phase, which is distinct from the dynamical phase. So, this is the dynamical phase. It tells you how the system evolves with time, looking at the solution of the time dependent Schrodinger equation. So, the coefficients have the same modulus as the previous one at the initial time, except for a phase which is called as the dynamical phase. So, these are the relationships that we have got. The modulus remains unchanged, but the relative phases are different. Okay? Why? Because the phase has got the energy in it. So, the energy of the different states are different. So, the relative phases are different. So, if you have a pure state to begin with, okay, if you have a pure state which is a particular eigenstate of A, then it is going to remain in the same state. There is only phase modulation, and if it is an eigenstate of some operator, some measurement which is compatible with the measurement of energy corresponding to an operator which commutes with the Hamiltonian, then it will continue to be a simultaneous eigenstate of the Hamiltonian and that measurement. So, it will remain in that. So, it becomes a constant motion, right. So, this is what is true for a pure state. Now, is this true also for a superposition state, for a mixed state? Because it is only the coefficients change only the phases, but a superposition has got so many of them, right, and each has got a phase, but the phase of this is not the same as the phase of that. So, there will be interference terms. Okay. So, you can carry out a measurement on pure states of operators or measurements which are compatible with the measurement of energy, which are operators denoted by operators which commute with the Hamiltonian, because commuting operators have got simultaneous eigenstates, non-commuting operators do not have simultaneous eigenstates. So, they cannot be diagonalized in the same basis. So, let us ask what will be the expectation value of some operator B which does not commute with the Hamiltonian. Okay. Now, this is an interesting situation. Keep this in mind, that if we are not talking about the time dependence of some measurement which really does not commute with the Hamiltonian. Nonetheless, the system to begin with is in a pure state, it is in an eigenstate of an operator which commutes with the Hamiltonian. So, it is in an energy eigenkette, it is an energy eigenkette, right. So, it is in a pure state. So, if you now find its expectation value, which is given by this, all right. So, this is a question we are asking, what is the expectation value? If you know the expectation value at t equal to 0, what will be the expectation value at a later time? Is it going to be the same or is it going to be different? So, all you do is to put in the state at time t can be obtained from the state at time 0 by operating on this state by the time evolution operator. Do this also on the adjoint vector and get the expectation value at a later time. But that is not an issue, because we have got the explicit form for this time evolution operator, which is this exponential operator, right. And notice that because this is an energy eigenkette, this operator operates on this, giving you an eigenvalue having the same form, which is e to the minus I e t over h cross, right? This will also give you the same, and those are no longer operators, those are just numbers, and they can be pulled to the left or right any which way, they will cancel each other, right? And that gives you a wonderful result that the expectation value of this operator, even when it does not commute with the Hamiltonian, at a later time remains the same as it was at the initial time, even if B does not commute with H, and even if B did not commute with A. All right. So this is an amazing result, because we are now talking about starting out with pure states which were energy eigenstates, and it is for this reason that these are called as stationary states, because the expectation value of any operator, okay, does not change with time if the state initially was a pure eigenstate of an operator which commutes with the Hamiltonian. Okay, so these are stationary states, and we know that how do these stationary states evolve with time? They evolve according to e to the minus I omega t, or E over h cross t. Okay, so that is the time evolution of the energy eigenstates. On the other hand, if the initial state was a mixed state, then it is a superposition, right? And then you must put all the components over the complete basis set, and now the cross terms do not drop out. Okay? So now because of these cross terms you have got these oscillations. So e to the I, you have got this difference Ea prime minus Ea double prime, and because of this you will have these cosine and sine terms, these oscillatory terms, and as a result of which this is no longer going to be the same as it was to begin with, which is why you call it as a non-stationary state, because of these oscillatory terms. So now you understand the difference between what is a stationary state and what is a non-stationary state. So now we are coming to some interesting questions. We now know how a quantum state evolves with time. We have reconciled with the fact that okay, classical mechanics cannot work because you cannot represent, you cannot measure position and momentum simultaneously, you cannot describe the state of a system by position and momentum. Description of the state of a system by a point in phase space must be dismissed. It has to be replaced by its description by a state vector in the Hilbert space, and then you examine how it evolves with time, and how it evolves with time is what we have just discussed. But then classical mechanics seems to work. We use it in everyday life all the time, right? To solve most of the problems in our day-to-day life, and we should therefore ask, why does classical mechanics work? So this is an interesting question, and I am going to discuss this in this class, in the remaining part of this class, and also over some of the next few classes. So let us begin to get an answer to this, that if you accept that the law of nature is quantum mechanical, which you have to, and then now you are trying to understand why classical mechanics works, then begin with the quantum mechanical equation. So we have written the time dependent Schrodinger equation. We also complex conjugate it. So there are two equations we have, A and B. We do a little bit of simple algebra. You multiply equation A by psi star and equation B by psi, and then take the difference, cancel the common terms, okay? All right. So the idea is very simple. You have to focus on the concept, all right? The details you do have to work out, because if you don't do it in your notebooks yourself, you will not have the confidence that you can do it right. But I don't prefer to do it on the board and let you copy what I am writing on the board, because when you are copying from the board, you are only copying, you are not learning. I want you to learn, which is why I don't use a board, so that you can concentrate on the idea over here. What is the idea over here? You begin with the Schrodinger equation, take its complex conjugate, multiply the first by psi star, the second by psi. Any schoolboy can do this algebra and take the difference, right? So I don't have to spoon feed this by writing this step by step and showing you how to do this. Take the difference. This is what you get after cancelling the common terms. And look at the term on the right. You can get it as divergence of what is there in the rectangular box, and on the left you get it as the time derivative of a product of psi star psi. Okay? This is again an algebra which a high school kid can work out. All right? If you have any difficulty because you think that I am going too fast, please stop me. The idea is simple, right? So what do you have? You have got the time derivative of the probability density given by the divergence of this function. And how many times have you seen this relation earlier in different courses, right? This is the equation of continuity, right? You have seen this in fluid mechanics, you have seen this in electrodynamics, and now you are seeing in quantum physics, right? In fluid mechanics, we use classical mechanics. In electrodynamics, we used classical electrodynamics, Maxwell's equation, there was no quantum mechanics. And now we are seeing it in quantum physics, all right? And we ought to wonder as to what is common between quantum and classical. Classical seems to work in many situations, it certainly works in our everyday life. It works in many situations, and here we get a result in quantum mechanics which does not seem to be any different from what we have seen in classical mechanics, and we have seen this in fluid mechanics and electrodynamics, and now we see in quantum physics, and it is a very genuine quantum result. In fact, it is responsible for some extraordinary quantum effects. This result, just because it is similar to classical mechanics, is not wrong, it is very correct. Not only that it is correct, it is able to explain many quantum phenomena for which there is absolutely no classical analog. Okay, so you can integrate this equation, use the Gauss's divergence theorem, okay, and you can seek again an analogy with the classical phenomenology, right? And this is what pops up as a very brilliant theorem known as the Ehrenfest theorem. So Ehrenfest was a great mentor, great physicist, one of the best of his times, and you might want to read about his biographical sketch. He had a very challenging life, a very difficult one, but I don't want to get into that. But I think sometimes it is important to know that people, when you see them as professionals, you know, sometimes in their personal lives they go through very different kinds of challenges, and that is something which no human being can ever escape. And when you go through your own challenges, remember that, okay, there were others also in similar situations and they did so well. Some of them didn't do all that well. So Ehrenfest is one of those who had a tragic end, but I don't want to get into that. So we now continue to discuss this correspondence between motion of a classical particle and a quantum particle. So you look at the expectation value of the position operator, okay. So get the expectation value of the position operator. I have sandwiched the unit operator twice on the right hand side. You can recognize it. that the unit operator is inserted twice. You see it? And now you get the eigenvalue of the position operator, and you can move that left or right any which way because it is no longer an operator, and use the orthogonality of the position eigenstates, but these are continuous space. So, you need to do a Dirac delta integration, and using the Dirac delta integration you are now left with a single triple integral instead of two triple integrals. Okay? So, this is after the Dirac delta contraction, and you get the expectation value of the position operator. Okay? So, now take its time derivative, and here you are taking the time derivative of three things. This is time dependent, this is also time dependent. The time dependence of this state vector, this is nothing but the wave function, right. This is the coordinate representation of the state alpha, which is the state function psi alpha r, right. So, I am using the Dirac notation and the wave function notation combined, right. And the time dependence of this state function is given by the Schrodinger equation, and this is the time dependence of the complex conjugate of that. So, you can get both of these from the state function. R itself is not time dependent, right. So, you take this as a product of these three terms, one of which is independent of time, and this is just like taking the time derivative of a product of two or three functions, which is one function times the derivative of the second plus the derivative of the second times the first function, right. So, you go ahead and do that. So, you have got the time derivative of the first function times the remaining part. This part is the remaining part, and then the time derivative of psi alpha. So, you get these from the Schrodinger equation, put them in, cancel the common parts. The algebra is simple. It takes a click of the mouse to show the result, but it takes a few minutes, and I can pause for you to do that or trust that you will work it out. The choice is yours. All right. So, you cancel the common terms, and essentially what you get is that the time derivative of the expectation value of the position operator, it can be r or x or y or z and so on, and here you have got these two terms. So, you have got these are complex conjugates of each other. So, it is like taking a plus ib minus a minus ib, right. So, you will get imaginary part of the complex number, right. That is what you have at the bottom of the slide. So, please work it out, and now you use the fact, this is a little bit of clever algebra that we use. Not everybody might think about it, but the smart ones do. All right. What is the derivative of the product of these three functions? X multiplied by psi star multiplied by del psi by del x. It is these three terms. Okay. Right. In each there is a derivative of one of the other two, and the remaining two come as multipliers. And this term is then the left hand side minus the other two. This is the term in which you are interested, because this blue term comes over here. Okay? So, you replace this in the integrand by these three terms, but you really do not need all the three terms, because you are interested only in the imaginary part, and this middle term does not have any imaginary part, this is real. This is del by del x of psi star, this is del by del x of psi, right. So, you can forget about it. So, you are interested only in the imaginary part, and dropping this part, the remaining terms are here. You have these two terms, this one and this one. So, the first one is this, the second one is this, right. Got it? Very easy to make a careless mistake when doing this. I have made those mistakes a number of times, all right. I am not sure if this one is right. So, it is something for you to work out and check out, all right. So, now you have these two terms, okay, one coming from this part and the second coming from this part, which I bring to the before I bring this to the next slide. I can already handle the first term because I see that I need to consider psi star at plus infinity and also at minus infinity, and for bound states it goes to 0. So, I can just throw that term, I can forget it. So, I have got only the red term to move to the next slide. Okay? So, that is what I do. Only the one term which was red, it has now changed color, but it is still the same. Okay? And this is the expectation value, the time dependence of the expectation value of the position operator. Okay? But what is minus I h cross del by del x? It is the momentum operator. So, now you have got a result which is very similar to classical mechanics, because if you think of these terms, what you have on the right hand side is the expectation value of the momentum operator divided by the mass. So, what is momentum by mass in classical mechanics? It is the velocity, right. And on the left hand side you have the time derivative of the expectation value of the position operator. And what is the time derivative of position with respect to time in classical mechanics? It is the velocity. So, you get the velocity on both sides, right. But this result is completely quantum mechanical and it has a pseudo classical structure, right. And this is the Ehrenfest theorem, that there is a certain correspondence between quantum mechanics and classical mechanics, and it sort of explains to us or gives us some hint about why classical mechanics works, all right. But there are deeper reasons than this which I will be discussing in the next few classes. So, I will stop here. If there is time we can take a few questions, otherwise I can take the questions next at the time of the next class as well. But this is the Ehrenfest theorem, and Ehrenfest was a student of Boltzmann. Boltzmann, as you know, committed suicide. Ehrenfest also committed suicide. He was very troubled. He had a son who had Down's syndrome. So one day he went with a gun, shot his son, and then shot himself. So it was a very tragic end, but a brilliant person. He mentored Uhlenbeck and Gauss-Schmidt, and I believe he also mentored Koopmans, after whom the Koopmans theorem in Hartree-Fock formalism is named. Thank you very much.